On the Theory of Compound Colors by James Clerk Maxwell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. On the Theory of Compound Colors with reference to mixtures of blue and yellow light by James Clerk Maxwell. From the Report of the British Association, 1856. When we mix together blue and yellow paint, we obtain green paint. This fact is well known to all who have handled colors, and it is universally admitted that blue and yellow make green. Red, yellow, and blue being the primary colors among painters, green is regarded as a secondary color, arising from the mixture of blue and yellow. Newton, however, found that the green of the spectrum was not the same thing as the mixture of two colors of the spectrum, for such a mixture could be separated by the prism, while the green of the spectrum resisted further decomposition. But still it was believed that yellow and blue would make a green, though not that of the spectrum. As far as I am aware, the first experiment on the subject is that of M. Plateau, who, before 1819, made a disc with alternate sectors of Prussian blue and gamboge, and observed that, when spinning, the resultant tint was not green, but a neutral gray, inclining sometimes to yellow or blue, but never to green. Professor J. D. Forbes of Edinburgh made similar experiments in 1849, with the same result. Professor Helmholtz of Königsberg, to whom we owe the most complete investigation on visible color, has given the true explanation of this phenomenon. The result of mixing two colored powders is not by any means the same as mixing the beams of light which flow from each separately. In the latter case we receive all the light which comes either from the one powder or the other. In the former, much of the light coming from one powder falls on particles of the other, and we receive only that portion which has escaped absorption by one or the other. Thus the light coming from a mixture of blue and yellow powder consists partly of light coming directly from blue particles or yellow particles, and partly of light acted on by both blue and yellow particles. This latter light is green, since the blue stops the red, yellow, and orange, and the yellow stops the blue and violet. I have made experiments on the mixture of blue and yellow light, by rapid rotation, by combined reflection and transmission, by viewing them out of focus, in stripes, at a great distance, by throwing the colors of the spectrum on a screen, and by receiving them into the eye directly, and I have arranged a portable apparatus by which any one may see the result of this or any other mixture of the colors of the spectrum. In all these cases, blue and yellow do not make green. I have also made experiments on the mixture of colored powders. Those which I used principally were mineral blue from copper and chrome yellow. Other blue and yellow pigments gave curious results, but it was more difficult to make the mixtures, and the greens were less uniform in tint. The mixtures of these colors were made by weight, and were painted on discs of paper, which were afterwards treated in the manner described in my paper On Color as Perceived by the Eye, in the Transactions of the Royal Society of Edinburgh, Volume 21, Part 2. The visible effect of the color is estimated in terms of the standard colored papers, vermilion, V, ultramarine, U, and emerald green, E. The accuracy of the results and their significance can be best understood by referring to the paper before mentioned. I shall denote mineral blue by B and chrome yellow by Y, and B3Y5 means a mixture of 3 parts blue and 5 parts yellow. Given color B8, 100 equals standard colors 2V, 36U, 7E, coefficient of brightness 45. Given color B7, Y1, 100 equals standard colors 1V, 18U, 17E, coefficient of brightness 37. Given color B6, Y2, 100 equals standard colors 4V, 11U, 34E, coefficient of brightness 49. Given color B5, Y3, 100 equals standard colors 9V, 5U, 40E, coefficient of brightness 54. Given color B4, Y4, 100 equals standard colors 15V, 1U, 40E, coefficient of brightness 56. Given color B3, Y5, 100 equals standard colors 22V, minus 2U, 44E, coefficient of brightness 64. Given color B2, Y6, 100 equals standard colors 35V, minus 10U, 51E, coefficient of brightness 76. Given color B1, Y7, 100 equals standard colors 64V, minus 19U, 64E, coefficient of brightness 109. Given color Y8, 100 equals standard colors 180V, minus 27U, 124E, coefficient of brightness 277. The columns V, U, E give the proportions of the standard colors which are equivalent to 100 of the given color, and the sum of V, U, E gives a coefficient which gives a general idea of the brightness. It will be seen that the first admixture of yellow diminishes the brightness of the blue. The negative values of U indicate that a mixture of V, U, and E cannot be made equivalent to the given color. The experiments from which these results were taken had the negative values transferred to the other side of the equation. They were all made by terms of the color top and were verified by repetition at different times. It may be necessary to remark, in conclusion, with reference to the mode of registering visible colors in terms of 3 arbitrary standard colors, that it proceeds upon that theory of 3 primary elements in the sensation of color which treats the investigation of the laws of visible color as a branch of human physiology, incapable of being deduced from the laws of light itself, as set forth in physical optics. It takes advantage of the methods of optics to study vision itself, and its appeal is not to physical principles, but to our consciousness of our own sensations. End of On the Theory of Compound Colors by James Clerk Maxwell. Read by Avai in October 2010.